Hello. Everyone. Right. And let me share the screen. So today we're going to do physics. We're going through some of the problems from the exam practice. Okay. So I wouldn't say it's a difficult one, but just yeah, we'll do some problems. Maybe at some point we won't get sidetracked and I'll go through something else. But overall, I've chosen several problems which I would like to go through with you. So what I wanted to ask, have you had your mock exams, your December, January mock exams already, or are they ahead? Can you answer in the chat, please? Physics Thursday. Ooh, okay. So yes, maths next week. Haven't had them yet. Okay. Had one in 2 weeks. Okay. So the timing is not that bad. I was afraid that you would all have your mocks in the first week of January, and then this assignment is coming in too late. But it looks like it's quite on time, which is good. So the assignment is very different from what you normally do in COMPOS. So let's get to it. So these are just exam practice from different exam boards, as you have seen. Maybe it would be nice just to see a different approach to the problems. The problems have been tweaked slightly. That means they're a tiny bit harder than normal. Okay, so the first problem, which is problem number 2. A metal ball leaves a ledge of height h above the ground at velocity v. The ball hits the ground at distance r away from the ledge. It's proposed that r is given by the formula, where g is the acceleration due to gravity. Verify this formula and find the constant q. I mean, this is an experiment, but it has great applications. Well, it has some applications which I'd prefer it didn't have, such as throwing bombs, because when a bomb is thrown, it is thrown horizontally, and then you very much need to know where it will land. Okay, it has some other applications as well, such as dropping things from a plane in general. Yeah, doesn't have to. It could be boxes of food. Doesn't have to be. Doesn't have to be something horrible. So yeah, B. You throw it, and you are interested in this distance. Of course, you're interested in this distance r, which is called the range. You need to know how far from the target you need to release it, or you need to fling it in order for it to land where you want it to. So this is not a random experiment. Yeah, it's not just throwing coins off the table. It is has great it has applications. Some of them I'm repeating myself. Some of them are not great. So, and we need to work out what Q is. So let's work it out. And this is the height. The height, and it will travel like this. And the aim is to look at the horizontal movement and the vertical movement separately. So horizontal motion, horizontal motion. Horizontal motion is a constant velocity. So the displacement in the x direction is equal to the velocity in the x direction multiplied by time. Well, we know that the displacement is r. The velocity in the horizontal direction is v, and t is something that we really want. Yeah, we need t. So usually you find t from the vertical motion. Vertical motion. Vertical motion is a free fall. So free fall. And because it's a free fall, it's constant acceleration. And if it's constant acceleration, then you can use suvat. Okay, so just the logic here. So suvat. You can use equations of motion, the one that we studied in COMPOS, of course, or you can just use the good old suvat. So the displacement. So we need to choose a direction. So I'm going to say that up is positive. Up is positive. Is positive. Yeah, Ben, I'll answer your question. Just give me a moment. The answer is pretty much always. Pretty much always. Up is positive. So S is minus H. Yeah, minus H. That is important. U is 0. U is the vertical velocity, which is 0. Final velocity, well, we don't know, and we don't really need it, so we can cross it out. Acceleration is minus g, and t is the thing we're looking for. So why are we looking for t? Well, because we need t. We need t here. So that's why this is what we're looking for. So we need a formula with no v. So we use the formula S equals ut plus 1/2 at squared. So S is minus h. U is 0. Acceleration is minus g, minus 1/2 gt squared. And from here, you can work out that t is 2h divided by g. And this is what you can plug in here. So you put that into here. And from here, you get the range is equal to v multiplied by, oh, sorry, the square root, of course. Thank you. Thank you. Root 2h divided by g. Right. So q is equal to 2h from here. So comparing to r is equal to v multiplied by q over g. Q is equal to 2h. Okay, so that's the answer. When won't the acceleration be constant? Well, the answer is pretty much always, because as a matter of fact, if you throw something from a tall building, The acceleration is not going to be g. It's only going to be g at first, and then it will gradually decrease. So the acceleration would be g, well, which is 9.81. It will gradually decrease to 0 if you throw something from a very tall building or from an airplane. If there's no air, of course, the acceleration will be like this. But that's not how it works. That's not how. Okay. So we use SUVAT when we ignore air resistance. And if we ignore air resistance, that's how it is. It looks like this. It's constant acceleration. So this is no air resistance. And this is with air resistance. And if the velocity is quite interesting. Velocity is quite interesting as well, because the velocity versus time, if there's no air resistance, it looks like this. No air resistance. And if you have air resistance, like this, air resistance. And what is this? Can somebody draw a line like this? What is this? Terminal velocity. Yes. V terminal. So Arman, it depends. So the question is, does it mean that assuming constant acceleration all the way, we're very far from the actual answer? If we're dropping a coin off the table, you will be incredibly close to the real answer. If you're throwing a coin off the top of the Empire State Building, then you'll have a completely different answer. Does that make sense? Because if you're dropping off the table, you're looking at this situation, and the graphs are identical. And if you are throwing it off a mountain, then it's like this. We are using constant acceleration because the model is so elegant and simple. It's a quadratic equation. Because introducing air resistance, so somebody's equations of motion, if equations of motion, if A is not constant, well, they look similar. So let's say acceleration is a function of t. Okay, well, acceleration is a function of t. Therefore, the velocity is going to be the integral of acceleration with respect to time. So usually we say acceleration is acceleration is 9.8. Yeah. 9.81. And then velocity is the integral of 9.81 dt, which is equal to 9.81 t plus c, where c is the initial velocity. It's 9.81 t plus initial velocity u, which can be written as u plus at. Ooh, do we recognize something? Okay. So if acceleration is constant, then it becomes this. But if it's not constant, it's this. It just happens to be that if acceleration is constant, the integral is very easy to calculate. It becomes this. Okay. Making sense? Any questions here? Ben asking perfectly good questions. Let me finish this. So the displacement then, the displacement is the integral of the velocity dt with respect to time. And if you do it here, the displacement is the integral of u plus at dt, and it becomes ut plus 1/2 at squared. Well, it's t squared over 2, because that's the integral of t, yeah, plus c, where c is the initial displacement. Yeah, so initial displacement. So s is equal to, so s0, the initial displacement, plus ut plus 1/2 at squared, which is also a very familiar formula. Well, we take the initial displacement, so change in displacement is ut plus 1/2 at squared. Another very familiar formula, right? Acceleration. If you're falling from a tall building, the acceleration does tend to 0, just like a skydiver. A skydiver, when the skydiver jumps, their acceleration tends to 0. So you reach a maximum velocity of about 70 meters per second. So skydiver. Skydiver. Top speed is about 70 meters per second, which is a lot. A car on a motorway is 30 meters per second. And acceleration drops from g at the beginning. At the beginning, you accelerate with g, and then to 0. At some point, you reach terminal velocity and you're falling. Whilst you're falling, your acceleration is 0, so nothing can happen to you. Well, I tried indoor skydiving, and the worst thing is that your helmet hurts when it tries to fly off your head. So nothing can happen to you. But when you hit the ground, you go in about 0.1 second, you go from 70 to 0. And your acceleration, once you touch the ground, is 70 minus 0. Well, 0 minus 70 technically, but divided by 0.1. Well, that's not. Oh, yeah. Okay. 700 meters per second squared. So the mass of your body is 70 kilograms. The force that you experience is 70 times 700, which is about what, 49,000 newtons. So the equivalent of an elephant on your on top of you. Okay, so does that answer your question, Ben? Yeah, so acceleration is what is the thing that gets you. Acceleration is the acceleration, well, is the damaging bit of any accident. Sunburn. Yes and no. Because the atmosphere, the question was, aren't higher heights not more dangerous once you've reached terminal velocity? The thing is, because if you look at the jump, I think it was performed in 2012 by the skydiver. He went from the stratosphere to the ground, and he broke the sound barrier. Now, if you're a skydiver, I said your top speed is about 70 meters per second, but he broke the sound barrier, which is 300 meters per second. So how does that make sense? Now, he was jumping from the stratosphere where the air is very thin and the air resistance is smaller, so the top speed is greater. So if you jump from a very tall, from like I think he jumped like from 30 or 40 kilometers, which is way much more than any skydiver. And he was falling. At some point, he reached, well, about 400-ish meters per second, which is way more than the maximum speed you can achieve close to the Earth. Now, when you start reaching the Earth, the density of the air starts to quickly increase. It increases exponentially. And because it increases exponentially, the air resistance, well, also increases exponentially. But you might not have enough time to slow down to 70. So falling from falling from space, yeah, imagine the ultimate thing would be you're falling from deep space. You have such a high speed as you enter the atmosphere that you don't have enough time to slow down, and you actually end up hitting the ground at a higher speed than the 70 meters per second. Okay. So extreme case, you are a meteor falling from Jupiter, and you enter the atmosphere at 28 kilometers. At 15 kilometers a second, and you just burn up in flames. You won't reach the ground. Fun stuff. Okay, the next one is problem 4. A roller coaster. Roller coaster consists of a set of carriages, such as the combined mass of the carriages and the passengers is 2,600 kilograms. Assume the roller coaster works by flinging the carriages from point A at a particular velocity, v. Which is the minimum velocity required for the carriages to reach point C? Do you all want to have a go at this problem and or just tell me how to do it? Feel free to use use the mic. At higher heights, not more. The kinetic energy needs to be equal. Yes, they need to be equal. Where? At which point? From A to B. Yes, exactly. So the kinetic energy at A must be enough for you to reach B. Does anyone have an answer? What's the speed? Ooh, Alfie, yes, very good. 28.7, yes. Is everyone on board with this? Please type 0 if you don't understand how to answer this question. The beautiful thing is that this does not depend on the mass, as a matter of fact, because the kinetic energy at A, so when you're at A, you're moving with velocity v, and you need to reach the top, which is height 42, and your kinetic energy, yes, the kinetic energy at A, 1/2 mv squared has to equal to the potential energy at B, mgh. M cancels out, v squared equals 2gh, v equals square root of 2gh, which is 28.7 meters per second. Very good. What is the minimum velocity required to point in 28.7? It was realized the force required to do this could be dangerous, and so it was rebuilt using a chain to pull the carriages. Yes, 28.7 is about 70 miles per hour. So yes, it is dangerous to pull the carriages from A to B. So the motor pulling in the chain has a power of 65 kilowatts, and it takes 32 seconds for the carriages to reach point B. What is the efficiency of the motor? So the efficiency is the useful work. Efficiency is the useful work divided by energy input. Energy input. So the motor has a power of 65 kilowatts and it takes 32 seconds. So energy input is the power multiplied by time. And the useful work is the work done reaching the top, which is mgh. Oop, oop, oop. Okay. MGH. Okay. And so 2600 times 10 times 42 divided by 65,000 times 32 and 2600 times 10 times 42 by 32. 0.525. I recommend leaving the answer like this, but if you want it as a percentage, it's 52.5%. But both answers are equally valid. Yeah. My personal preference is 0.525. C. Once the carriages reach point B, they're released and fall down to point C. If the track is almost entirely straight and at an angle of 60 degrees to the vertical, how fast are the carriages moving at point C? Interesting. Okay, so I love this question. Well, I think so. This is a modified question. The original is must be different. Okay. But yeah. So you have a track. You have a track at an angle. And it looks like you need to use conservation of energy to find, well, to find the, normally, to find the velocity at C, you would say energy at C is equal to energy at B. G at B. So you would do 1/2 mv squared plus mgh at C equals mgh at B. Yeah, so that's the normal way how you would find the velocity at C. But it tells you that there is a coefficient of friction which will slow the carriage down. So we can't use that because there will be energy lost due to friction. So you would have to, you could do it like this. You could do it like this plus energy lost to friction. But how are you going to calculate the energy lost to friction? I mean, there is a way, but in this particular case, this one phrase turns an energy conservation question into a SUVET question. So let's see. So the carriages are here, and it's 60 degrees, and it starts with 42 and ends with 12. So we can say 60 degrees to the vertical. So this is 60 degrees. And this is 42 minus 12. That's 30 meters. So this is 30. And if this is 30, this must be 60 meters because this is 30 degrees. 30 degrees. The side opposite to the 30-degree angle is half the hypotenuse. Yeah, in a right angle triangle, the side opposite to the 30 degrees angle is half the hypotenuse. Therefore, this is 30, this is 60. Okay, so the forces The forces is mg. There's the normal reaction force. And there's the friction force, which is mu n. So acceleration along the x-axis, so the x-axis goes this way, acceleration along the x-axis, so mass times acceleration, is, so mg okay. Let me redraw that. Don't like this. Remember, I was talking about making the angle smaller. So this is 30 meters. So this must be 60 meters. So if you have a force, this is the mg force. This is the normal reaction force. And there's the friction force, mu n. Okay. So this is the x direction, and this is the y direction. So max, the acceleration in the x direction, mass times acceleration in the x direction. So we split mg into components. This is 30. This is 30 degrees. This is 60 degrees. So this is 30. So this is mg sine 30. This is mg cos 30. So max is mg sine 30 minus mu n. But n is equal to mg cos 30. So it's mg sine 30. So may mass, sorry. So we've written this down. Now we use the second Newton's law for the vertical, for the y direction. And it's n minus mg cos 30. And we know that the acceleration in the y direction is 0. Okay, so n minus mg cos 30 is 0 because there's no acceleration in this direction. And therefore, we have n is equal to mg cos 30. So this force is equal to this force, which is quite straightforward, but yeah. So this is equal to mg sine 30 minus mu n, mu mg cos 30. Okay, so from here, acceleration is equal to g sine 30 minus mu cos 30, which is g multiplied by 0.5 minus 0.2 times mu 0.2 cos 30 is 0.87 cos 30. 0.87, yes. So 0.5 minus 0.2 times answer, which is 0.327 g. This is the acceleration. And how fast the carriage is moving at point C. So here, because acceleration is constant, we can use suvat. Suvat. So displacement is 60 along the x direction. Suvat in the x direction. So u is 0. V is the question mark. Acceleration is 0.327 g. And t is we don't know and we don't care. So from here, we use the formula without the t. So which is v squared equals u squared plus 2as. So v is equal to 2as. So 2 times 0.327 g multiplied by 60. Multiplied by 2, multiplied by 60, and multiplied by g. Well, we can use 10 for g. So 300, that's v squared, 392. 392 meters squared per second squared. So v is equal to square root of that, which is 19.8. 19.8 meters per second. Perfect. So this is the velocity. This is the velocity at c. Okay. Well done. Any questions? Any questions? I've been talking. I've been talking for a long time. Perhaps while I'm doing, maybe we'll leave like 15-20 minutes at the end, and maybe you have a question you are struggling to do, and we can go through that. Okay, if you're preparing for your mocks and there's a question which you don't know how to do, I'm happy to go through that. Okay. You just need to think how you're going to send it to me. Okay. The next question. A student wants to measure the friction between a puck and the surface of a table. They push the puck and release it from point R, and the puck travels a distance d before coming to rest in the center of the target. They record the following measurement. Mass of the puck, 0.35. Initial speed is 0.78. Distance traveled by the puck is d. Calculate the coefficient of friction between the table and the puck. If they could remeasure one of the three values above with more precise instruments, which one would you recommend to give the greatest improvement in accuracy? Okay, so there's lots of things going on here. Well, first of all, just the physics bit. How would you link? So you need to find mu. That's what you're looking for. How would you link mu mass u d link? How would you do it? Feel free to switch on the mic and tell me. Anyone? Any ideas? Yeah, absolutely, Alfie. That's what you need to do. You need to calculate the work done by friction, and then what do you do with that? With the work? I mean, well, yes, the friction force is coefficient times the normal reaction force. That is true. But how do you find the work? If you don't know the force, how are you going to calculate the work? Yes. Hold on. We need to use something that is called the work energy principle. We haven't done this yet in COMPOS, but you should have done that in school. So it's called the work energy principle. And it looks like this. The change in kinetic energy of an object is equal to the total work done. Total work done on that object. In other words, the change in kinetic energy is equal to the work done. And this is a very important principle. What it says that the work done on an object changes the kinetic energy of an object. And if you think about it, it makes perfect sense. If you take a tennis ball and you throw it, you have done work. You push the tennis ball and it moves. So you've done work increasing the kinetic energy of the tennis ball. When you catch a tennis ball, you're doing work to decrease the kinetic energy of the tennis ball. When you're riding a bicycle, the brakes do work to reduce your kinetic energy. Your muscles do work to increase your kinetic energy. And so on and so on. Okay. So the change in kinetic energy of the puck is equal to the work done by friction. So the change in kinetic energy of the puck is equal to the work done by friction. All right, the kinetic energy of the puck, so it's final kinetic energy minus initial. So final kinetic energy is 0, minus initial kinetic energy is 1/2 mu squared. And the friction force is mu times n times the distance traveled. Well, technically times cosine of the angle between the displacement. So the displacement is this way and the force is that way. So the angle is 180 degrees. So cosine 180, and that's -1. And here you have 1/2 mu squared equals minus mu n d, and n is equal to mg. So it's equal minus mu mg d. M cancels. You have mu is equal to 2 1/2 u squared divided by gd is equal to u squared divided by 2gd. That's mu. Now now it's the interesting part. You need mu with the uncertainty. And there's a principle that the percentage uncertainty is equal to the sum of the percentage uncertainties of all the values. When you multiply or divide, the percentage uncertainties add. Are you aware of that? Do you know how to deal with percentage uncertainties? Perfect. Yes, you do it in physics. You should. So it's the percentage uncertainty in U twice because it's squared, so you add it twice, plus the percentage uncertainty in G plus the percentage uncertainty in D. Okay. The percentage uncertainty for G is not given. So, well, if I was doing an experiment, I would include it. Here, I would say we can ignore it for now at least. So what to say? The velocity 0.78. So the percentage uncertainty in U, uncertainty in U is equal to 0.01 divided by 0.78, which is 1.28%. 1.28%. So that's 2.56%. So 2.56%. If you like, I don't want to confuse you. In an A-level question, it would be very clear where you need to take the percentage uncertainty and where you don't. Armand, significant figures for percentage uncertainties, I would say 3. Okay, there's no requirement to have a certain number of significant figures for the percentage uncertainty. And they won't mark you down if you get a different value. Now the percentage uncertainty for D is, now this is written wrong, so it has to be 160. Okay, 160. So it's 0.001 divided by 2.160. 0.001 divided by 2.160. Which is 0.04. 0.6%, which is very small. And uncertainty, yes, so as I said before, I don't want to confuse you because it will be clear that you need to take the percentage uncertainty for the gravity, for the gravitational constant, because if the gravitational is the acceleration due to gravity is given to 9.81, this implies 0.01 uncertainty. But in an exam question, they will tell you what to do with G. So you don't need to worry about it. So for now, just simply assume that it is 0. And so 2.56 plus 0 plus plus D 0.046%. So in total, that's 2.60%. Oh, very nice. 2.61, sorry. 2.61%. Okay. 2.61%. And you can see that the greatest contributor is, of course, the U, the initial speed of the puck. This is what you need to measure more accurately in order to get a better result. And you find mu. So mu is u squared, which is 0.78 squared divided by 2 times 9.81 multiplied by d, which is 2.16, which gives us fraction 78 squared divided by 2 times 9.81 times 2.16, 0.0144. So mu is 0.0144 plus or minus, so 2.16%, so times 0.0261. So that's 0.0000374. And now you just clean this up. You just clean this up and you say, okay, well, if it's this, this has to be rounded to one significant figure. So we cross this out. So 0.0144 plus or minus 0.0003. And we can see that this is rounded appropriately already. Okay. So you have to have the same decimal places in the uncertainty and in the original value. Oh, sorry. It's truncated because it's not. Yes, it's rounded, of course. It should be rounded. Okay, if you're struggling with uncertainties, Isaac Physics, they have a fantastic section on uncertainties. Okay, Isaac Physics uncertainties, and yeah, really good practice. Okay, what else do we have here? So I think I'll do one more problem today, and then I'll ask you if you have any problems that you would like me to go through. A 3-meter long wire is stretched between points A and B. A mass 100 grams is placed in the center of the point of the wire drops by a distance of 6.34 centimeters. What is the spring constant of the wire? Now, what is the spring constant of the wire? Basically, what it says that the wire behaves like a spring. Yeah, we don't very often hear the spring constant of a wire, but if you apply a force, if you apply a force to the wire will stretch. So this delta x, so the force is equal to K delta x. So as you can see, the wire has this length, but now it has become longer. And what you need to do is you need to find the tension in the wire, and you need to find the extension of the wire, delta x. And then you can work out K. So K will be the tension divided by the extra length. How would you find the extra length of the wire? Pythagoras, yeah, by all means. Because we know that this is 1.5 meters, 1.5 meters. We know this is the y, and this is, well, let's call it L. So L is equal to, no, that's a very bad idea to call it L, because L is, assumes the length of the wire. Let's call it, I don't know, A. So A squared, well, okay, I hope you all know how to use Pythagoras. It's going to be y squared plus 1.5 squared, which is square root of 6.34 squared plus 150 squared. This would be a number very close to 6.34 squared plus 150 squared. 50.1393 centimeters. Now you need to be very careful here because you're finding the difference. Well, it's obvious here that you need the extra length. So delta x, the extra length of the wire, is is 2 times 0.13393, because we are looking for the whole wire, the extra length of the wire. So minus 150 times 2, so 0.268 centimeters. That's the extra length. And now we need to find the tension. Of tension, you should be familiar with this because we've done this a couple of times in the assignments. So we look at the forces acting at C. So we have the mg force, we have the tension force, we have another tension force. So we break the tension into components. So this is T. So this is T cos alpha. This is T cos alpha. and this is T sine alpha and T sine alpha. Right, so we need cos alpha and sine alpha. So mg, Newton first law, that T sine alpha is equal to mg. The vertical forces are equal. Yeah, vertical forces. Vertical forces. And here we can find T. T is equal to mg divided by 2 sine alpha. Sine alpha, we will draw a triangle to find alpha. Alpha is this angle. This is 1.5, sorry, 150.1393. This is 6.34. So sine alpha is equal to 6.34 divided by 150.13393. Now, interestingly, there's an important thing here. If you do tan alpha instead, tan alpha is going to be 6.34 divided by 150, which is pretty much the same. So because for small angles, sine alpha is approximately equal to tan alpha. And it's actually also approximately equal to alpha. That's another, this is a very important thing to know if you don't. So yeah, so tan alpha is this, so we just plug that in. So that's equal to 100 grams, so 0.1 kilograms multiplied by gravity, we'll take 10, 2 times sine alpha, 6.34, 150.13393, and 6.34 divided by 150 times 2. Okay, times 2. 11.2. 11.83 newtons. That's the tension, and then K is the tension divided by the extra length, which is 11.83 divided by the extra length, 0.00268 meters. Here, be very careful here. And divided by 0.00268, and we get 4,400 newtons per meter. So approximately, of course. This is the spring constant of the wire. Sam, this is only true for when alpha is in radians. In radians. If you take just the first two, it is true for degrees as well. Degrees, or radians. But the whole thing is only if alpha is in radians. Otherwise, radians and degrees would be the same thing, which is not true. Right, we'll continue with those. We have another week to do, so we'll carry this on. Does anyone have a problem that you'd like me to go through from your preparations? No? Okay. Yeah, can you tell me, can you send it to me somehow? Telegram, Slack? In general. Are you sending it? Ah, okay. Mm-hmm. Oh, okay. Mhm. A smooth surface consists of a quarter circle sheet joined to a smooth horizontal plane, a light rigid rod. So this is mechanics. Looks like maths. A smooth surface consists of a quarter circle. Quarter circle sheet. So quarter circle sheet. Joint in onto a smooth horizontal plane. A line ridge rod with two small equal masses, each end lies in a vertical plane. Oh, this is the surface. Okay. Okay. Unfold. 1.18 of the circumference. 1/8 the circumference. When released, the rod and mass will slide along the smooth horizontal plane. Calculate the maximum speed if the rod and mass remain in the same vertical plane. Radius of the circle is 3.4 meters. 3.4 meters. 8.4 meters. Okay, well, this is the conservation of energy question. So what happens is the right. So the bottom mass is at height equals 0. Height equals 0. And the top mass is, well, at a certain height above the ground. Let's call it h. Well, what you need to do is to find the maximum speed of the rod and mass. Well, calculate the maximum speed. Okay, well, the maximum speed is when all of the potential energy is turned into kinetic. So you would have them down here connected, and they're traveling with velocity v. Okay. So there's several different approaches you can take. You can take the change in the position of the center of mass. You can say that the kinetic energy of the system is equal to the change in potential energy of the center of mass. Yeah, this links very nicely into the previous topic, center of mass. Or you can just say kinetic energy is equal to, well, no, change in kinetic energy is equal to the change in the total potential energy. The second way is simpler. You don't have to bother with finding the center of mass, even though it is in the middle. But it's just the kinetic energy. So the potential energy of this mass does not change. It goes from 0 to 0. The potential energy of this mass changes from h to 0. So the kinetic energy is equal to mg h capital. And the kinetic energy is 1/2 times 2m, because there are two masses and they are identical. Two masses, yes, two masses. 2m times g is equal, times v squared. Times v squared equals mgh. So m cancels, 2 cancels, v is equal to square root of gh. This is the maximum velocity. And then we just use geometry, which we love, to find the height. Okay, so what can we do about it? Well, this, first of all, a better diagram. So this line is vertical. So then we have this. Okay, so we need to find the height h. Okay. We know that this distance is 1/8 of the circumference. So it doesn't mean that it's 1/8 of a circle, because that's the straight edge. One eighth of 2 pi r. So that's pi r over 4, in fact, pi r over 4. And this is r. This is r. Can we use a right angle triangle here? Ideally, yes, but we don't know this side. Can we do it without finding the angle? No, it seems like you can't. So we need this angle. We need this angle. And because the height is equal to 1, so pi r over 4 multiplied by cos theta. And to find this angle, we can use the cosine rule to find this angle. We can use pi r, so r squared, using the cosine rule. R squared is equal to r squared plus pi r over 4 squared minus 2 multiplied by r multiplied by pi r over 4 multiplied by cos theta. R cancels. We've got pi squared r squared over 16 is equal to pi r squared over 2 cos theta. Pi cancels, r squared cancel, 2 cancels 8, cos theta equals pi over 8. So that it means pi r over 4 multiplied by pi over 8. So the height is pi squared r over 32. And you just plug that in. So that's h square root of g times pi squared r over 32, and it gives you something. Hope that makes sense. Is that correct, though? Well, this is not ideal because it says the separation of masses is 1/8. Are we talking about the separation along the curve, or are we talking along the line? If it's along the line, it's not 45 degrees. But if it's along the curve, then it would be 45 degrees. So yeah. And yeah, this is a very weird question. Is it? I've never seen anything like that. I mean, it's a bit clunky. The 1/8 is not very helpful here. It's just confusing. And it does look like a math question rather than a physics question. Okay, anyways, I hope that was useful. Next week, we'll do a similar session. If you have any questions, do let me know. I'm happy to go through. I'll set some time aside so we can go through a couple of problems. Otherwise, we'll be doing some of the problems from the assignment. Okay. So those of you who have not had their mock exams, good luck. Don't stress too much about it, but do well. Okay, see you everyone.
Thank you.
Bye.